For the first time in human history, we know the exact half second the moon gets hit, and this time, the whole world can watch. In 4 days, on August 5th, 2026, at 34 minutes and 32.9 seconds past 6 a.m. Universal Time, a piece of rocket hardware the size of a 5-story building will slam into the lunar surface at 5,400 miles per hour, carrying the energy of roughly 3 tons of TNT. Astronomers have published a timestamp accurate to the 10th of a second, 11 months in advance. This is not a forecast with error bars measured in days, the way a hurricane landfall prediction works. This is one of the most precise appointments in the history of spaceflight, and unlike every other prediction humans make about the sky, this one cannot be moved, altered, or stopped by anyone. The object carries the catalog designation 2025-010D. It's the second stage of a SpaceX Falcon 9 rocket that launched on January 15, 2025, carrying 2 commercial moon landers. One of them, Firefly Aerospace's Blue Ghost, touched down successfully in Mare Crisium that March, the first fully successful commercial lunar landing in history. The other, Espace's Resilience lander, went silent about 90 seconds before touchdown that June and crashed. The rocket stage that delivered both of them had no destination of its own. Its job finished, it was left in an enormous lopsided orbit around Earth, swinging out as far as 510,000 kilometers and back to roughly 220,000, completing a full loop every 26 days. The moon orbits Earth at about 385,000 kilometers, meaning the rocket's path crossed that same distance twice on every single lap. For 18 months, the stage and the moon kept narrowly missing each other, close pass after close pass. This collision was never inevitable. What finally locked the rocket onto a collision course wasn't a malfunction or a maneuver, it was sunlight, the same faint, constant push that also complicates the tracking, slowly nudging a dead machine toward a world it was never built to touch. The stage itself is about 12 meters long and 4 meters wide. Mostly hollow, empty aluminum lithium fuel tanks with a single engine bolted to one end, with an estimated mass somewhere between 3,900 and 4,900 kilograms, depending on which research team's estimate you use. It has had no fuel, no power, no working thruster, and no radio since January of 2025. Every meter of its path since then has been governed by exactly 2 forces, gravity and sunlight. Here's something worth sitting with. This collision wasn't discovered by NASA, the Space Force, or any government tracking network on Earth. It was found by one independent astronomer named Bill Gray, who runs a project called Project Pluto, whose orbit computation software flagged the impact back in September of 2025 while processing observations collected almost incidentally. Military radar catalogs tracked debris in low Earth orbit down to lost tools and dropped equipment. But radar strength falls off according to something called the inverse fourth power law. Push an object 400 times farther away, and its radar echo returns roughly 25.6 billion times fainter. At lunar distances, the world's radar networks are effectively blind. The only instruments capable of spotting high-flying junk like this are asteroid surveys, telescopes built to hunt genuinely dangerous space rocks that occasionally catch a slow-moving point of light that turns out to be a discarded rocket, plus a scattered community of amateur astronomers. The asteroid surveys that flagged this rocket weren't looking for it at all. To them, high-flying junk is a nuisance, a false positive contaminating a search for objects that could actually threaten Earth. By late February of this year, 1,053 observations had accumulated from observatories in Mississippi, Utah, Beijing, and England, plus additional surveys and backyard telescopes. Those observations matter enormously for the prediction's precision, because the one force nobody can compute perfectly is sunlight. Solar radiation pressure keeps nudging the tumbling stage, and how hard it pushes depends on exactly how the object is tumbling. Gravity is known to extreme precision. The sunlight push is why a June update moved the predicted impact point 170 kilometers northwest, and why the most recent July update moved it by only a couple of seconds and about 10 kilometers. The prediction is converging. The appointment stands. So why can't anyone stop it? Not because of physics, because of absence. There's no engine burn coming because the stage has no fuel. There's no command to send because it has no radio. And there's no rescue mission being organized because no such mission exists anywhere on the planet. No agency, no treaty, no office in any government has the assignment of managing dead rockets in the space between Earth and the Moon. Let's talk about the physics of the impact itself. Traveling at roughly 2.43 kilometers per second, carrying up to 4,900 kilograms of mass, the stage will hit with about 14.5 billion joules of kinetic energy, equivalent to roughly 3 tons of TNT, about 15,000 sticks of dynamite, delivered to a single point on the lunar surface in a fraction of a second. The stage will be moving at what would be Mach 7 in Earth's atmosphere, arriving at an angle of about 31 degrees above the local horizon. The expected result is a brand new crater somewhere between 17 and 30 meters across, smaller than an asteroid carrying equivalent energy would create, since the stage is a hollow shell rather than a solid mass. The excavation, though, is genuinely substantial, on the order of 450 cubic meters of lunar rock and soil, roughly 500 tons, about 800,000 pounds of the moon thrown outward with no atmosphere to slow a single grain of it. This is where the impact shifts from accident to genuine scientific asset. Every crater scientists have ever studied on any planetary surface came from an impactor whose mass, speed, and angle had to be estimated after the fact. Next week's crater is fundamentally different. The projectile's size, mass range, velocity, arrival angle, and arrival time are all known in advance down to the half second. That makes the fresh scar near Einstein crater a genuine calibration point for the crater, scaling laws scientists use across planetary science, including the models behind planetary defense calculations, the same math that determines what a genuinely dangerous asteroid would do to a populated area. If you find this kind of precisely tracked, real-time science genuinely fascinating, that's exactly what this channel exists to bring you. So consider subscribing if you haven't. Now here's the question that decides whether Wednesday morning becomes a global spectacle or a quiet footnote. Will anyone actually see it happen? The answer splits into two very different pieces, a flash and a cloud. The impact flash itself, the split-second burst of light at the moment of contact, will almost certainly be invisible from Earth. The impact site sits in full lunar daylight, and no impact flash has ever been convincingly detected against the moon's sunlit surface, not even by professional observatories. This impactor is also slow by lunar standards. Natural meteoroids strike the moon at 10 kilometers per second and up, some past 70, and the fraction of impact energy converted into visible light climbs steeply with speed. At 2.43 kilometers per second, this stage sits at the bottom of that scale, a faint glow buried in daylight. In October 2009, NASA deliberately ran this exact experiment, steering a spent rocket stage into a lunar crater timed for darkness, with large telescopes trained on the site. From Earth, they saw nothing. If a deliberately staged impact under ideal viewing conditions produced no visible flash, a dead rocket hitting a daylight surface won't beat it. But the flash was never the real prize. What comes up afterward is. Because the impact point sits almost exactly on the moon's western limb, the visible edge as seen from Earth, any dust thrown upward could appear, silhouetted against black sky, hugging the bright rim of the moon. Research teams modeling this scenario project an ejecta curtain climbing 15 to 20 kilometers above the surface, with a central spike of fast debris potentially reaching 75 to 100 kilometers high, and material spreading roughly 183 kilometers outward from the impact point. In the optimistic modeling scenario, the simulated cloud could outshine the dark sky background by several orders of magnitude in the first few minutes, potentially lingering for around 10 minutes. Bill Gray's own more conservative back-of-envelope calculation assumes slower ejecta, rising only about 3 kilometers before falling back, separating from the moon's bright edge by a mere 1.5 arc seconds, marginal for any telescope on Earth to resolve. The wild card is speed. If a meaningful fraction of the debris leaves the surface faster, the event becomes unmistakable. The honest answer is that nobody on Earth currently knows which scenario will play out, which is exactly what makes next Wednesday morning a genuine live experiment, 11 months in the making, with the whole planet invited to watch it run. There's also a genuine chemical mystery riding on this event. The stage's fuel tanks are an aluminum-lithium alloy, and observers are being encouraged to try a narrow filter tuned to the lithium emission line at 678.8 nanometers. If that faint lithium signature shows up in the debris cloud, it would be a first in history. The chemical fingerprint of a human-made impactor read directly from the light of its own ejecta cloud. To understand what to expect, it helps to look at the only real precedent, March 4th, 2022, the first predicted lunar junk impact in history, also identified by Bill Gray. That object was initially misidentified as a Falcon 9 stage from 2015, then re-identified after independent observers matched its paint spectrum to Chinese rocket hardware, the upper stage from China's Chang'e 5T1 mission. China has never publicly acknowledged the impact. That stage struck the moon's far side, completely hidden from every telescope on Earth, which is exactly why this upcoming impact is unprecedented. It's the first predicted human-made lunar impact ever positioned where we can actually watch it happen. When NASA's Lunar Reconnaissance Orbiter photographed the 2022 site 3 months later, it revealed something nobody predicted, a double crater, 2 overlapping pits spanning about 30 meters total, implying significant mass concentrated at both ends of the impacting object, mass that was never disclosed on any public manifest. That anomaly has never been explained. Next week's Falcon 9 stage carried its heavy engine at one end and nothing comparable at the other, so the prediction calls for a single crater roughly 17 meters across. When the Lunar Reconnaissance Orbiter eventually photographs the fresh scar near Einstein crater, That image becomes a verdict. One crater closes the physics cleanly, 2 craters would reopen the 2022 mystery on an object we thought we understood completely. For anyone wondering whether the moon itself is at any risk, it absorbs impacts like this constantly. In spring 2024, a natural meteorite gouged a 225-meter crater into the lunar surface, 10 times the diameter and roughly 1,000 times the ejecta of this upcoming impact. And nobody on Earth noticed it happen in real time. Apollo mission planners deliberately crashed the upper stages of Apollo 13 through 17 into the moon as seismic experiments, and the instruments recorded the moon ringing like a bell afterward. The moon will be fine. And what's genuinely new next week isn't the impact itself, it's that this one is ours, tracked and predicted in advance, with humanity able to watch it happen for the first time. Before wrapping up, it's worth directly addressing a claim already circulating online, that this impact is somehow deliberate, that the stage is being intentionally aimed at the moon. The tracking data dismantles that immediately. The stage has been unpowered for 18 months with no propellant and no working engine capable of steering anything. The predicted impact point drifted 170 kilometers between 2 recent updates, pushed by nothing more than sunlight. Nothing AIM behaves that way. As for questions about the object's identity, it's anchored to its January 2025 launch by more than 1,000 independent observations, with the full tracking record publicly available. Between now and August 5th, tracking updates will continue pinning the impact point down to within a few dozen meters and a fraction of a second. There's one genuine wildcard remaining, a small chance the refined impact point shifts enough to push the site over the moon's visible edge onto the far side, hiding the entire event from view. If it stays on the near side, the viewing geometry favors eastern North America and much of South America specifically, with the moon roughly 56% illuminated in a dark sky at impact time. You don't need a professional observatory. Backyard telescopes may be enough, framing the moon's bright disk just off the edge of your camera sensor, cutting the glare and recording at 20 frames per second or faster. There's also a quieter scientific experiment riding on this event beyond the visual spectacle. The research team organizing the public observing campaign is explicitly using August 5th to test a pipeline for precisely localizing lunar impacts, a modern descendant of the technique used during the Apollo era, when those deliberately crashed rocket stages were used to calibrate seismometers astronauts had left behind on the lunar surface. If the localization technique works cleanly on an impact whose time and location are already known in advance to this degree of precision, it becomes a validated tool for future lunar seismic networks trying to identify the location of unknown, undetected impacts. Whether the debris plume turns out to be visible or not, the underlying data from this event flows toward something scientifically useful either way, which is part of why researchers describe next week as valuable, regardless of how dramatic it does or doesn't turn out to look from a backyard telescope. This whole situation also exposes a genuine blind spot in how humanity currently manages the space between Earth and the moon. Roughly a dozen dead high-flying objects are currently known to be wandering that same general region, known only because one independent contractor happened to keep looking. More than 600 Falcon 9 rockets have launched to date, and most spent stages either fall back into Earth's atmosphere or get thrown into a permanent orbit around the sun. This particular one simply wasn't, and once it wasn't, it belonged to no tracking system on Earth. Compare that to how seriously space closer to home is managed. Low Earth orbit has collision avoidance systems, conjunction warnings, and debris catalogs updated daily. Cross into the volume of space beyond that, and essentially all of that oversight evaporates. The fix for this specific problem already exists and costs very little. It's called heliocentric disposal, using a spacecraft's last reserves of fuel to throw a spent stage into a permanent orbit around the sun, well clear of Earth-Moon space entirely. It was done for the stage that launched the James Webb Space Telescope. It simply isn't required by any regulation, so it isn't yet routine. With the current era of lunar missions producing more launches, more discarded stages, and more dead hardware crossing the same general volume of space, this upcoming impact functions as a low-stakes, real-world demonstration of a blind spot that won't stay harmless indefinitely as lunar traffic continues increasing in the years ahead. We'll be tracking the final orbit updates, the impact window, and the first images as they come in over the next several days. Thank you for watching, and I'll see you in the next one.